In this video, we're going to look at the central limit theorem. We're going to look at the central limit theorem for means and for proportions. Well, what is it? Suppose you have boxes that you are shipping and you have several shipments of these boxes a day. And the shipment follows a uniform distribution. That means that when we're talking about a uniform distribution, the probability of this happening versus the probability of this happening should be the same. They're equally as likely. So the boxes that we are shipping is between 200 and 600 grams. If we randomly select a package, we know that it's equally as likely, because of the uniform distribution, that the weight will be 200, 600, or anywhere in between. The mean, because it's a uniform distribution, we use the formula that we have the beginning plus the ending divided by 2, so the mean would be 400 grams. The standard deviation for a uniform distribution is the square root of the ending minus the beginning, the quantity squared divided by 12, so the standard deviation is 115.47 grams. Now imagine what we're going to do is for each shipment that gets sent out that day, or that week, or that month, we are going to choose 5 packages from each shipment. And say we have 100 shipments going out in a week's time, we're going to take 5 from each of those 100 shipments, and we are going to find the mean of those 5 packages from each shipment. We then have these means, they become the new data point, and so we're going to then look at the means of the means. And when I graph the means of the means as a histogram, it's going to look something like this. This is maybe, 5 packages, 100 sample means, and it's going to look something like this here. And then let's do this again. So now instead of taking 5 packages and 100 shipments, let's take 10 packages for 100 shipments. When we do that, this is what the graph looks like. Now, when I now have 100 pieces of data, and each one of the pieces of data is a mean, and because we're grabbing a larger sample size, the mean of my means, the mean of means, super mean if you will, is going to be closer to the 400, and it's going to have more of a normal or symmetrical shape. Now, if we choose a larger sample size, so let's now choose 30 packages, and we're still going to do 30 packages from each shipment. We have 100 shipments. We measure the mean. We then say, okay, the mean for each sample becomes the data piece for the mean of means, the bigger picture. And we end up with something that looks like this. It's more symmetrical, looks more like the normal distribution. And that's what the central limit theorem states. It says, hey, if we take and repeat this process over and over again, where my sample size is 30 or more, then I will have a distribution of known or unknown, it doesn't matter. We'll then take the means of each one of those samples, and those means become data pieces. We then find the mean of these new data pieces, and now my distribution, even though my initial one may not have been normal, will become normal. So when we're talking about the sample mean, this is the X bar, that is a statistic. The notation for the sample, or for the population mean, is mu sub x, that's a parameter. The notation of a sample standard deviation is S, that's a statistic. Remember, statistics are associated to samples and parameters are associated to populations. The notation for a population standard deviation is sigma, or sigma sub x. The sampling distribution of a statistic is the probability distribution of all possible values of the statistic that is computed from a sample size of n. This is a population of all the possible sample means when we're talking about the central limit theorem. The sampling distribution of the sampling means, X bar, is a probability distribution of all possible values of the random variable computed for a sample size n from a population with mean mu and a standard deviation sigma. Now, suppose capital X is a random variable with some distribution. It can be any, and we don't care what it is. Using a subscript that matches a random variable, we'll have the mu sub a, which is going to be equal to the mean of this random variable. We're going to have the sigma sub x, which is the standard deviation of this x. If you draw a random sample of size n, as n increases, the random variable x, which consists of all the sample means, will tend toward the normal distribution. Here is the notation. So this is now a capital X with a bar. So we're talking about some random variable, and we're talking about the means. And it's going to be approximately normally distributed as a normal distribution. And we use mu sub x as our mean. And our sigma that we will use will actually be the sigma sub x divided by n. So if we're given a sigma of 3, then we take and divide that by whatever our sample size is, the square root of it, and that's what we use for our actual standard deviation. That standard deviation is also sometimes called the standard error of the means. So it is the standard deviation of the sampling distribution of the sample means. The random variable, lowercase x, which is a particular mean, has a different z-score associated to it from any of the random variables with the capital X. The mean, a particular mean out of a sample, x bar is the value of x bar in one sample, and so the z-score is going to be the x bar minus your mu sub x divided by this calculated standard deviation. Typically, it's not the one that is given to us. The central limit theorem allows us to estimate the population by using sample means. We can bypass the fact that we don't know what the population distribution is. We can use it to determine the probability of getting a correct population mean. And we're going to find probabilities about x bar. We will treat it exactly as any other normal variable. My mu sub x will be mu, and my sigma sub x bar, this is a capital X bar, is going to be the sigma that is given to me divided by the square root of n, and we're either going to be using the normal dist or the normal dot dist. So let me just show you that on that. Let me get rid of that. So if I'm using the normal dot dist, then I don't find a z-score. I'm just going to say I've got this x, a mu, sigma, and I choose true or false. And then I do the norm dot invert. Now I need more than just the probability. I'm going to need my mu and I'm going to need my sigma. Should I decide that I want to use the norm dot s, if I'm using the norm dot s, then this is going to be equal to the norm dot s dot dist. And when I'm using the norm dot s dot dist, then I use a z-score, and then I'm going to either say true or false. Similarly, if I am trying to find a value that's associated to a certain percentile or a certain probability, that's when I do the norm dot s dot invert. And when I'm using this, I only use the probability, or the percentile. I don't need anything else. That's when I have the standard normal distribution, and the way that I can force myself into the standard normal distribution is to find the z-score. All right, and of course, here's my z-score here. This is how I'd find my z-score if I wanted to use the standard normal distribution. Most of the time, if I'd not asked for that, I probably will not find it. But you can add that. I just don't have it here. So I would recommend you have some sort of calculator that looks like this. I like to label everything. I have my x bar 1 and my x bar 2. These are some values a and b. These are the means, the sample mean that I am interested in, or the data point. We have the sigma, which is a population standard deviation, and then we have sigma sub bar. This is a calculated sample standard deviation, or the standard error of the mean. Sample size, you'll be given mu, you'll be given sigma, you'll be given n. We typically, unless we are not given n, we'll calculate our sigma sub bar, and the way that we do that is we're going to do an equals in this cell. We're going to grab the cell that has sigma, we're going to do the division symbol, we're going to type in SQRT, and we're going to grab the cell that has the sample size in it. From there, we will enter the first value that I'm interested in, and if I don't have any other value, then I'm going to get everything that I need right here. If I need to sandwich between two values, so say 2 and 4, then I would have this other value Smaller value goes here, the larger value goes here. Again, you may not have a second value, you may only be using this. Either way, what I'm going to do is if I want to know the probability of my random variable to be exactly my A value, my mean that I'm interested in, then I'm going to use the norm.dist. I'm going to grab the cell that has A, I'm going to grab the cell that has the mu sub x, and I'm going to grab the cell that has my calculated standard deviation or sigma sub x. This is the first and only time that we ever use false, and that's when I have equality. Otherwise, I'm going to use true, and that is when I go to the left, and when I go to the right, I just take 1 minus the 1 up above. So if I want to the right, I want the right tail, if you will, I just do 1 minus the left tail. If I'm sandwiched between two, then I'm going to enter some fourth of the value here, my B value. Again, this has to be bigger than this value. And this should say true, not false, because I am doing a cumulative, not an equal. So for the norm.dist, I grab my cell with a B, grab my cell with my mu sub x, grab the cell that is the calculator standard deviation or sigma sub x, and type in true. This will give me to the left. If I want between the two values, I will take the one I just calculated and I will subtract off the lower one. So let me show you what's happening with a picture that looks like this. So here's this normal curve. Here is where B is. Here is what A is. When I do the probability of capital X being less than B, I'm finding all of this. When I am finding the probability of my capital X being less than A, my lowercase a, then I'm finding all of this. The value that I want is this. So that's how come I take the probability of everything to the left of B minus the probability of everything left to the A, because that will take off this extra piece that I don't actually need. Now, if I want it on the tails, I want the outside tails. So if I come back up here, let me erase my picture. If I want the outside tails instead of the inside tails, say I want this side of B, this is B, and I want this side of A, then what I'm going to do is I'm going to do 1 minus a probability to the left of B, that's that number. And then I'm going to get that number, which is here, and I'm going to add it to the probability of less than A, and then I'm going to get those two tails. Now, suppose that I have a percentile or a probability, and I'm chasing a particular value, a particular mean value. Then I'm going to either use the norm.invert. I will enter my percentile, my mu sub x, my sigma sub x from up above. If I had found the z-score, then I would just need to know this probability here, and I would do the norm.invert, and then I would have just my percentile. Now, this is going to give me the z-score. It's not going to give me the particular mean, and so if I do that, if I use the norm.s, right? So I'm like, oh, I calculate my z-score. It's not going to give me my particular value that I'm interested in, because my z-score is going to be equal to my point of interest minus my mu divided by my sigma divided by the square root of n. So when I do the norm.s.invert, it's going to give me this. It's not going to give me that x. So what I would have to do if I'm using the norm.s.invert is I'd have to take that value that is calculated for me, multiply by the sigma divided by the square root of n, which, by the way, this is already done for us. This is my sigma sub x. And then from that, I would have to add on to my mu, and that will actually give me my x bar that I wanted if I am using the norm.s.invert instead of just the norm.invert. If I need to find the empirical rule, this will be my mu from up above. I'm either going to add or subtract a sigma, the calculated sigma sub x, or I'm going to add or subtract 2 of those, or I'm going to add or subtract 3 of those, just depending on what is required on my empirical rule. Now, what happens, and this could happen on your homework, what happens when you are given mu, you're given sigma, but not n? Well, what we do now is we're going to need to find the z-score, and notice since we can't do the sigma sub x calculation, so we don't have an n, we're going to use the z-score, so we use x minus mu divided by sigma, and then I'm going to use the norm.s, which is my invert, and then If I need it between two, then I'm going to copy whatever it is that's up here. So say I want to be less than x of 1 or greater than x of 1 but less than x of 2. I do a copy and paste. So I'm going to find whichever one that's appropriate here, do a Control C or Command C, but here I'm going to do a paste that says paste values only. So that's why you'll see these are green. That's the things I'm going to put in here. And then that's what I'm going to get. So let's take a look at my first example. I have a mu is 3, sigma is 1.5, n is 75. Find the probability that a particular mean is less than 2. So here's my graph. This is my mean, which is 3. And I want to know this probability. That's the shape because this is where 2 is. Now notice my mean is in the middle. So I'm going to go out to my calculator that I just went through with you all, and I'm going to put in my mean of 3. And I want the probability less than 2, so I would have, if I'm coming back up here, I would have put in this number right here. So here's my 3, my 1.15, this should be 75. Here's my 2. So I was playing around with it earlier. That's how come that doesn't match this very first example. And when I'm finding this, I end up with a very small number. I end up with 2.5 times 10 to the negative 14. So in other words, I get approximately 0. Now, for the next one where I want to know what is the 90th percentile, I would be using that calculator that I enter the percentile in. So I'm going to put in 0.9. And in the 90th percentile, the value, the mean that would be associated to the 90th percentile is 3.17. So that would be the data point that would be in the 90th percentile. A manufacturing company produces a commodity where the length of the commodity has approximately normal distribution. Cool. That means I don't really care what my sample size is. It is more than 30. But they're telling me it's normally distributed, so that makes my life easier. I'm going to have a 9.6 is the mean, standard deviation of 3.1, sample size of 46. So again, I'm going to go over to my calculator. I'm going to put all those numbers in appropriately. My mu sub x is going to be the 19.6. My sigma is going to be the 3.1, and my standard deviation, or my n, is 6. What is the probability the sample's mean length that you choose is greater than 19.6 inches? Well, that's kind of nice. 19.6 is right here, so that is my mean. And I don't have to do actually any calculations because 19.6 is the mean and it's right in the middle. And so the probability of my x being greater than or equal to, it doesn't matter, 19.6 is 0.5. What is the probability the sample's mean is between 19.6? So here is 19.6 and 20.5. Let's just assume this is 20.5. So that represents 20.5. So this is what I'm looking for. So I'm going to have 19.6 in my A. I'm going to put in the 20.5 for my B. And then the sandwich between them, because that's what I'm looking for, this. So this is the probability that 19.6 is less than the capital X, which is less than the 20.5. And my spreadsheet calculates that for me, and I got 0.4755. So slightly less than 10%. And that kind of makes sense because my sigma sub x is going to be 0.457. And you can see that I am actually more to go from 19.6 to 20.5 is about 2 standard deviations above the mean. So that 0.4755 makes total sense. If I want to go above 19.6, so here's my above 19.6, and I want to go above the 20.5, so that's this part right here. So this is the probability of my x, capital X, is less than 19.6, and actually my x bar is greater, or not my x bar, my capital X is greater than 20.5. Once again, I am going to put that down into my calculator, and what I end up with is that this is going to be equal to, close up parenthesis, this is going to be equal to 0.5245, and that makes total sense because I get more than, you get 0.5 here, and this is slightly more than 0.5. We don't want to add it all up, so that makes total sense. What is the mean? That is in the 80th percentile. So again, I'm going to get my spreadsheet out. I'm going to put now, instead of 0.9, I'm going to put in 0.8. And the mean is 19.985. So that is the mean that is associated with the 80th percentile. Now, the second part of this chapter is talking about sample proportions. So suppose you have a random variable of size n is obtained from a population, which the individual does or does not have a certain characteristic. The sample proportion, denoted as p hat, sometimes p prime, is given by the number that have the, quote, success divided by the total number of that sample. So x is the number of individuals in the sample, and p hat is the one that estimates the sample proportion, p. And you're going to see p hat is going to be those who have, quote, success, and those are the total of the sample size. So we assume that the samples are independent, and if they are, the first thing we have to do is make sure that n times p times 1 minus p, which is q. So n times q is greater than or equal to 10. Sometimes this check is n times p is greater than 10. And simultaneously n times q is greater than or equal to 10. The mean of the sampling distributions is going to be mu, which is n times my p, which is my p hat actually. And then my sample deviation of the sampling distribution, my sigma sub p hat, is going to be n times p hat q hat. Again, p hat is going to be those that have success over the number, and q hat is 1 minus p hat. So that's what we're going to use unless I'm trying to find probabilities about p hat. That means what I'm looking for is percentages around p hat. I use all of this by default unless I'm looking for probabilities around p hat. If that's true, then my mean is going to be my p hat. That's p hat. And my standard deviation is going to be p hat, q hat divided by n. So that should be p hat, or q hat divided by n. Either way, it doesn't matter. I'm going to be using the normal distribution, or excuse me, the binomial distribution, because binomial means I have two outcomes, success or failure. I'm going to choose my number a that I'm interested in, my n, my p, this is p hat, and I'm going to either choose true or false. Again, you're going to want to have some sort of spreadsheet. If for some reason you are not giving the percent of success, you might have something off to the side that says this is what I'm going to use. My y is the number of successes not given as a percent divided by the number of pieces in my sample so that I can actually find my p hat. If it's given to me, I don't need that part. So here's the actual calculator that I typically use. Notice I have the central limit theorem. I tell you what I should check, or it states it's a normal distribution. P, which is equal to P naught, sometimes noted as P naught. This is a population proportion of success. P prime, also noted as P hat, sample proportion of success. Q, which is equal to Q naught, which is 1 minus P naught. This is a population proportion failure. And when we see Q prime or Q hat, this is the sample proportion of failure. Sigma is the population standard deviation. Sigma P hat is the calculated sample standard deviation, also known as the standard error of the mean. This is not usually given as a percent. I'll show you further down in the calculators when it is given as a percent. It's a different kind of calculation. Mu is a numeric non-fractional decimal value used for population means. Okay, so p hat is either going to be given to me as a percent, or I'm going to use that calculator up above. My n will be given to me. My q hat is going to be 1 minus my p hat, and then my sigma p hat is going to be equal to the square root of p hat times q hat times n. Mu, which is going to be equal to my sample size multiplied by p hat. So in this cell, so let me back up. In this cell, I'm going to do 1 minus this to get me my Q hat. This one I'm going to type in equals SQRT. I'm going to grab this cell, and this cell, multiply them together. And for this cell, I'm going to do an equals. I'm going to grab the N cell, the cell that has N in it, and the cell that has the P hat. Now, suppose the value of interest that I have is a numeric. I'm not talking about percents. Let's say I've got 150. What is the probability that I'm looking for something that is 150 or less out of a sample size of 300, and 53% is expected to be success. So if I want it equal to, I use the binomial.dist and I use false. If I want the left tail, then I'm going to use the binomial.dist. I'm going to grab that A value, which is the cell that has 100. I'm going to grab the cell that has N, the cell that has P hat, and I'm going to type in true. If I want the right tail, I do 1 minus the left tail. Again, if I want to sandwich, here's my sandwich as before. If I want the tails, this is as before. And then, of course, excuse me, I have the empirical rule for numeric values, not necessarily percents. So what I know is that 68% will be between 150.355 and 167.66. It'll be my mu minus sigma p hat, or my mu plus sigma p hat, and then multipliers of 2 or 3 if I need to be 2 or 3 standard deviations. So here is my first example. We have Janice, Barbara, Kathy, and Roberta decided to carpool together to get to school. Each day the driver would be chosen at random, and we're going to select one of the 4 names. The carpool to school for 96 days. Use a normal approximation to the binomial to calculate the following probabilities. Round standard deviations to 4 decimal places. Find the probability that Janice is the driver at most 20 days. Cool. So we're going to use the theoretical probability, and Janice being chosen is 1 out of 4. So it's 1 out of 4 times. So that is going to be 0.25. So that is my P hat. P hat is success of Janet being chosen. Now, I have my mean. So let me go ahead and put everything in here. I'm going to have 0.25 for success of choosing Janet. We have 96 days, and so my mu right here in the middle is going to be 24. So that I use my calculator, my spreadsheet, my mu, it comes out to be 24. And we want to find the probability that Janice is the driver. P is going to be X as at most, so less than or equal to 20. So that's what I'm going to look for. So I'm going to put in 20 into my spreadsheet where my A value is. And I'm going to choose the one that is the left tail. So here's where, say, Janice is. I'm looking for this tail. The probability that Janice will be chosen at most 20 days, which is the left tail test, is going to be equal to 0.21. Oh, round to 4 decimal places. So make everything rounded 4 decimal places. So it's going to be 2.0 using my spreadsheet 65. So the probability of Janice being chosen at most 20 days is this. Find the probability that Roberta is driving is the driver more than 16 days. So because it's 1 out of 4, I'm still going to use my P hat as being 20.25. So P hat is still 0.25. Here's where my mean is. This is 24. And we want to know how often what's the probability? So probability of X being greater than or equal to 16. Remember, greater than and equal to, or just strictly greater than, has the same thing because this is a continuous. So now I'm going to put in my A value of being 16, and I'm going to choose the right tail. So the probability that Roberta is the driver more than 16 days, rounded to 4 decimal places, is 0.9655. So it's a high probability that she will have to drive more than 16 days. Find the probability that Barbara drives exactly 24 of those 96 days. Okay, so here is Barbara, or I mean, here is our mean, which is 24, and we want to know exactly, so I'm not left or right. So what I want is the probability of my random variable being exactly 24. So now I'm going to put in 24. And the probability of Barbara, because again, my p hat, there are 4 choices. My p hat is still 0.25. I'm going to get with a 0.0937. So about a 9% chance that Barbara will drive exactly 24 days. Now, based on past experience, here's my next example. A bank believes that 9% of the people who receive loans will not make payments on time. The bank has received and approved approximately 200 loans. What is the mean and standard deviation, the standard error of the sampling distribution? Because I don't have sigma, then I'm going to use a slightly different calculator. And I can't remember up above if I said it was n or sigma that I didn't have. It's sigma that I don't have. So since I don't have sigma, like I did in all the previous ones, it's like, hey, put in the sigma. We are going to use this calculator. So mu, which is equal to p hat, that is going to be our mean. Our sigma that we're going to calculate, this is going to be the standard error. We have n as a sample size, and we are going to be looking at things in the percents this time. So rather than the numbers before, I said, what was the probability that Roberta got chosen 25 times? You know, whatever it was. Now we have the mu, which is our mean. We have our n that's going to be given to us. We'll have our q hat. Our sigma hat is different now. This is going to be equal to the square root of p hat times q hat divided by n. This is a slightly different calculator for the sigma hat. And then, of course, I can use the empirical rule, taking my mean, adding and subtracting sigma p hat as appropriate in multiples of 1, 2, or 3. So it's slightly different. So let me just show you that so you can pause it or do whatever. These are all in the notes, however. Okay. So I'm going to go out to my calculator. I'm going to put in my mu of 0.09 because that's 9%. I have 200. And so my mean, my mu, is the 0.09. My sigma p hat, using the calculation of the square root of p hat times q hat divided by n, is a 0.0202. So what does that mean? Well, about 9% is the mean. And so if I go 1 standard deviation, which is 2% down and 2% up, I'll get 68%. Because I already have this already in my calculator, I know that if I take 9% and subtract 2.02%, I'm going to get 0, so as a percent, I should put it as a percent. So as a percent, not as a decimal, I'm going to get about 6.98 here. And then the upper bound would be 11.02%. So 68% of the time, the percentage of late payments will be between 6.98 and 11.02%. 95, that is 2 standard deviations away. This is going to be 4 looks like about 95. And then the lower bound would be 13.05 approximately. So this tells me that 98% of the time I can expect, if I was the banker, that I'm going to have between about 5 and 13% of the mortgage payments to be late. That's pretty much it for this video.